Welcome back to the continuation of the boundary layer analysis lecture. So, we are going to start this lecture by solving yet another problem where there are two velocity profiles is given, okay, one for the laminar flow here and one for the turbulent flow. Okay. This is for the turbulent flow. So, this is laminar and this is turbulent. We are going to the ratio of the displacement thickness delta dash by ratio of delta for laminar and the turbulent cases. Okay. All right, for two separate cases. So, we will start, we will go to the white screen and we will start doing the solution for laminar boundary layer. U by capital U is given as 3 by 2 minus y by delta minus y by delta minus half y cube by so let me just so yeah, so there is some mistake in my writing. So actually the laminar was U by capital U is equal to 3 by 2 y by delta minus half y cube by delta cube. This is laminar velocity profile, and therefore, by definition the displacement thickness is 0 to delta 1 minus u by capital U dy, and we substitute this velocity profile here and we are going to get integral of 0 to delta 1 minus 3 by 2 y by delta plus half y cube by delta cube into dy, and after integration which we are going to get y from 0 to delta minus 3 by 2 delta, and this is going to be y square by 2 0 to delta plus 1 by 2 delta cube y to the power 4 by 4 0 to delta, and the displacement thickness is going to be, this first term will be delta minus 3 by 4 delta plus 1 by 8, this is 8 delta. Okay. This will give us delta dash is equal to 3 by 8 delta, and this implies that delta dash by delta for laminar case is going to be very simple. This we have been doing anyways. Now we will do for turbulent boundary layer. U by capital U is the velocity profile is y by delta to the power 1 by 7. Okay. So, the displacement thickness by definition is 0 to delta 1 minus u by capital U dy, and we plug it in here. Okay. And therefore, what we get is integral 0 to delta 1 minus y by delta to the power 1 by 7 dy, or we get delta star as after integrating and putting the limit 0 to delta minus 1 by delta to the power 1 by 7 into 7 by 8 into y to the power 8 by 7 divided, no, okay, and this also goes from 0 to delta, and therefore this comes out to be, after limit delta, second term will be 7 by 8 into delta, or this is going to be 1 by 8 delta. Therefore, displacement thickness, and this is for turbulent so yeah, so this is for the turbulent boundary layer. All right, so this question is complete, and now we can proceed to another topic, that is von Karman momentum integral equation. So, what we do is we consider a uniform flow past a flat plate of width b. Okay. So, the width of the plate is b. So, this is the definitions are as usual, a uniform velocity u is coming and it strikes the leading edge here, and then the boundary layer would start to develop, and at the end of the boundary layer, where the boundary layer thickness is delta x, okay, there will be a shear stress developing tau w as a function of x. Okay. All right. So, we have written the, we have shown the figure again on the right hand side. So, what is the assumption? The assumption is that the pressure is constant throughout the flow field. The flow entering the control volume at section 1, here this is uniform, okay, leading edge of the plate. So, the flow entering the control volume at section 1 is the leading edge of the plate, is uniform, okay, and the velocity of the flow at section 2 here varies from 0 to u, and this happens because of the boundary layer. All right. So, this is the assumption that we start with. So, the fluid in the immediate vicinity of the plate makes up the lower portion of the control volume. So, you see the control surface here. So, we have chosen a control surface here. This control surface, it says that the fluid in the immediate vicinity. So, this one, you see the dash line, now I am marking it red dots. This is the lower portion of the control volume, okay, and the upper surface of the control volume coincides with the streamline just outside the edge of the boundary layer. So, you see, so this is the topmost surface of the control volume. Now, if we apply the conservation of linear momentum along x direction for steady flow, what do we get? So, do you remember this equation from somewhere? Just a quick thought. Yes, It is Reynolds transport theorem that we did in week number 2. All right. So, the conservation of linear momentum along the x direction for the steady flow gives us sigma fx is equal to rho integral uv dot nda plus rho uv dot nda. That are the two surfaces at two different surfaces. Okay, for steady flow, therefore, there is no time variation. We can also write, so drag sigma fx is equal to minus of f drag. So, drag will happen because of this shear stress here, okay, and this is, as I told, is due to tau w. All right. Now, this equation number 4 can be written as minus f drag. So, I will, so this is the equation. We write rho u minus u into bh is plus integral 0 to delta u square b dy. All right, and this gives us equation 5. What we did it? We just substituted the equation 4 and put in the velocities, and this is section 1 where uniform flow was there, right, and here the boundary layer, and now you can understand why two different forms of momentums we have written. Okay. All right. All right. And this is minus u because the velocity vector makes an angle of 180 degree with the normal. So, this was the control surface, you remember, something like this, right. So, the velocity was in this direction and the normal to this surface was here, all right. So, that is why 180 degrees. Or simply we multiply it minus 1 on both sides, this becomes f drag is equal to rho u square bh minus rho integral 0 to delta u square b dy. This u is capital, this u is small. Okay. From the conservation of mass, the flow rate through section 1 here must equal the mass flow rate through section 2. That is correct. All right. Therefore, we can write u into h. So, u into h is equal to integral u dy. If you assume, thickness, element of thickness, and at distance y the velocity is u, so it becomes u dy. Very simple. So, if we multiply rho ub to both side of the equation 6, this is equation 6. So, we get rho u capital U square. So, we multiply this term rho capital ub. So, for the left hand side become rho capital U square bh, all right, is equal to rho b capital U small u dy, and this is integrated to 0 to delta. Now, if we substitute this equation 7 into equation number 5, I will take you to equation number 5 again. So, this was equation number 5 with the drag force equation. What we get? F drag is going to be rho b integral. So, the idea was to substitute the first term in equation number 5 by this. So, it will be written as rho b integral 0 to delta capital U small u dy, and this was already there in the equation number 5. All right. All right. Or simply if we take some terms outside and take the common, it becomes force drag, F drag will become rho b integral of 0 to delta u multiplied by the velocity deficit into dy. Simply, in other word, if you take, if you, or I mean you multiply this side by capital U square and divide this, so it won't make a difference, capital U, then you get rho b u square integral of small u by capital U into 1 minus u by small u by capital U dy. All right, very simple. Simply I will write multiply and divide RHS with capital U square, then you can get this. So now what is this? You remember? This is the momentum thickness theta. Remember from our last lecture? So F drag can simply be written as rho b capital U square theta, where rho is the density, b is the width of the plate, capital U is the free stream velocity, and theta is the momentum thickness. If we differentiate both sides with respect to x, this equation, equation number 8, if we differentiate, we can get df drag by dx is equal to simply rho b u square, other things are constant, become d theta dx, right, and we can write this as equation number 9. Also we know that this drag was due to integration of shear stress over the entire area, integral tau w b dx. We get, if we differentiate this with respect to x, we get simply this integration sign will go and it will become df drag by dx is equal to tau w b, all right. And then you know what needs to be done, we are going to substitute, I mean equate equation number 9 and equation number 10, right, and we get tau w is equal to rho u square d theta dx. I will just, I mean very elementary, but okay, let me show you, rho b u square capital, okay. So rho b capital U square d theta dx is equal to tau w b. So b will get cancelled here, right. So tau w will become rho u square d theta dx. All right. So this is what it is written here. And this famous equation is called von Karman momentum integral equation, a core component of this module and the hydraulics in general. All right. And this, the beauty of this equation is it can be applied to both laminar and turbulent boundary layers. So this is the general equation, because we have not at any point in time assumed whether the flow is laminar or turbulent. All right. Now what are the boundary conditions at the plate? It's very simple. U, the velocity at the plate is going to be 0, correct. The second condition is d square u by dy square at y is equal to is 0. This is the second boundary condition. Now the third boundary condition is at the top of the boundary layer. This means that the velocity at the top of the boundary layer is the free stream velocity. And this is no slip, and the velocity gradient at the top of the boundary layer is going to be 0. All right. Now we will use all these boundary conditions in our further analysis. Okay. With this, we are going to start solving one problem. The question says, an approximate expression for the velocity profile in steady 2D incompressible boundary layer is given by the following function. Okay. Now we have to show that the profile satisfy u at, I mean we have to see that the boundary conditions are actually satisfied or not. These are the velocity profile. All right. And here eta is y by delta. Okay. So, to solve the question, we are going to go to the white screen. So, we have been given u by small u by capital U is equal to 1 minus e to the power minus eta plus k into 1 minus e to the power minus eta minus sin pi pi eta by 6, and this is for eta greater than or equal to 0 or greater than or equal to 3. Also u by small u by capital U is equal to 1 minus e to the power minus eta minus k e to the power minus eta, and this is for eta greater than or equal to 3. Here eta is given as y by delta. So, actually when y is equal to 0 implies eta is equal to 0. All right. When y is equal to delta, eta is equal to 1, and when y is equal to infinity implies eta is equal to infinity. So, first part where now u by capital U at y is equal to 0 can be written as u by capital U at y is equal to 0 is equal to u by capital U. All right. Simply y is equal to 0 means eta is equal to 0. All right. Therefore, small u by capital U at eta is equal to 0 can be written as 1 minus 1 plus k into 1 minus 1 minus 0. All right. So, u by v is equal to 0 implies, oh sorry, not v, u by capital U. Implies u at y is equal, I will go to the white screen again. Okay. So, simply u at y is equal to 0 is 0. thus proved. Okay. For y is equal to infinity, eta is equal to infinity. Therefore, u by capital U is equal to 1 minus e to the power minus k eta to the power. Therefore, u is equal to capital U minus capital U k e to the power 1 minus eta. Now, u at y is equal to infinity is equal to u at eta is equal to infinity is equal to u minus u into 0 minus u into k into 0. So, therefore, u at y is equal to infinity is equal to u, and thus second part is also proved. Okay. So, now del u by del y is equal to del u by del eta into del eta by del y, implies del u by del y is equal to del y of y by delta into del u by del eta. Okay, so is equal to 1 by delta into del u by del eta. This is another equation. All right, and we have seen the equation number 1 before. That u was, which we just wrote it, u is equal to u minus k e to the power minus eta minus e to the power minus eta. This was 1 actually. Fine. So, differentiating both sides of equation 1 with respect to eta, we get del u by del eta is equal to, this is equation 1, equal to u e to the power minus eta. All right. Plus u k e to the power minus eta. That is equation number 3. Now, del u by del y at y is equal to infinity is equal to del u by del y is equal to n is equal to infinity using both, and this comes out to be 1 by delta u e to the capital U e to the power minus infinity plus u k e to the power minus infinity, and this comes out to be 1 by delta 0 plus 0. Thus del u by del y at y is equal to infinity 0. So there is one more part left for del square u by del square u by del y square, but I will leave it up to you to prove it. Try yourself at home using this maths that we have seen. So this concludes the problem for today, and we will start with another problem, problem number 5, when we resume next. Thank you so much.